So we've already introduced the concept of density, but we just want to end chapter 1 talking about this a little bit more in depth. So density is a derived unit. We have to do a mathematical equation to get this. And so it's the physical property then that relates to the mass of an object to its volume. So we've got mass per unit volume. Anytime you see this per in an equation, this represents a ratio or division. So it's going to be mass over the volume. So most substances contract when they're cooled and expand when they're heated. Water is an exception to this rule as well. So water, while it also has a very high specific heat, water also expands when it freezes, and this makes ice, or the solid form of water, less dense than the liquid. So ice is going to float on liquid water. Most things are not that way. Most solids would sink in their liquid counterpart. The liquid usually is less dense than the solid form of the compound. So density then can be written as an equation. It's going to be written as mass in grams over the volume, and the volume is going to either be represented as a milliliter or the centimeter cubed. So you remember these two units are equivalent to one another. 1 milliliter equals 1 centimeter cubed. So you can write this in either unit and you don't have to do any conversions between them. So which one is heavier, a ton of feathers or a ton of bricks? Oh, that's a trick question. They're both the same. A ton is a ton. But you can see that the representation of that ton in space is going to be different. The ton of feathers is going to take up a lot more space or a lot more volume because the feathers are less dense. The ton of bricks is going to be much more compact, and it's going to take up less space to give you that same weight. So if two objects have the same mass, the one with higher density is going to be smaller. It's going to fit into a smaller compressed compartment. It is more dense. So these are just some density examples. We can see that density is actually defined on the density of water as well. So at 4 degrees Celsius, the density of water is at its densest point. It is 1.00 grams per milliliter. This is in the liquid state. So we get the highest density of water is right before the water is going to freeze and move into the solid state. So water in the solid state is actually less dense than it is in the liquid state at 4 degrees Celsius. So you can see the solid ice is going to be much less dense than the liquid water. So ice has a density of about 0.917. So then you can see the density of gold much higher than water. The density of air much less than water. Helium, also a gas, much less dense. So if you release helium, helium is going to float through the air because it's less dense than the air. And that's why if you fill up a balloon with helium, it wants to float, right? It's less dense and it's going to lift up off the ground. So these are just some examples of different densities, and we'll take a look at some density problems here in a minute and give you a little bit of practice with doing some density. That will end chapter 1. Be sure to walk through the chapter summary. It gives a good overview of what we've covered in chapter 1 and the focal areas that you'll need to know for the exam. So you should be able to determine what matter is and how it's classified. Look at the different phase changes between solid, liquid, and gas. Know those definitions. How matter can be classified as being either a pure substance or a mixture. Then understanding how chemical elements are represented. Their 1 or 2 letter codes, and know the first 4 rows of the periodic table plus those extra elements that we indicated within the lecture. I think we had silver, gold, mercury, lead, and iodine as the major constituents that you should be familiar with. You should be familiar with what kinds of properties that matter has, the difference between physical properties and chemical properties, how you identify those, and then how you measure physical quantities of things. So looking at our definition for mass, length, volume, and temperature, and then our factor label method being utilized to convert between these units, and then measuring how good your reported measurements are. So looking at things like significant figures, scientific notation, problem solving using our factor label method, and then doing some calculated measurements as well, such as temperature, if we need to calculate between different temperature units, and density. And then these are a list of keywords that you should be familiar with for Chapter 1 as well. Alright, so I'd like to go over a density problem too, because we can use density to help us find the mass or the volume of a substance if we know one or the other unit. So we're going to use table sugar as our example, and we were given in our table in our lecture the density of table sugar. So the density is going to equal 1.59, and density is always written in grams per milliliter. So that's our density for our table sugar. So if I tell you that you have 802 grams of table sugar present, I want to know what the volume is of that sugar. How much space is it taking up? So I tell you you have this much, and I want to know what is the volume. So we have a unit of volume that's measured in our density. So our density is now going to act as a conversion factor. So we can relate, so mass and volume are related by the density. So this becomes our conversion factor, and we can say that for table sugar, we can either say 1.59 grams per 1 milliliter. So again, if you have no coefficient out here, that's just going to be 1. Or we can write it with the mils on the top. We could say 1 milliliter of sugar is going to weigh 1.59 grams. So this becomes our conversion factor that we can use to figure out what our volume is going to be. So our volume is measured in liters as the base unit. So if we start with 802 grams, which conversion factor are we going to need to use? The mils on top or the grams on top? We want to get rid of grams, and we want to get volume, or milliliters in this case. And so we want the milliliters to be on top and the grams to be on bottom so that we can get rid of them. So if we say times 1 mil over 1.59 grams, this is going to cause our grams to cancel out. So these guys will disappear. And if we do this calculation, we will find that this answer is equivalent to 504 milliliters. So we would say 802 grams of table sugar should take up 504 milliliters of space. And that's an example of a density problem.